Now we're going to look at the relationship between force and acceleration. We've seen that force and displacement are related to the change in energy of motion, which is associated with a change in velocity. So if we have a mass m and a force F net being the net force acting on the mass m, then we're going to have an acceleration that's equal to the net force divided by the mass. The acceleration and the net force are vectors. They have magnitude and direction, and the direction of A is going to be parallel to the direction of F net. The acceleration will be parallel to the net force. Okay? So let's say we have a net force of 200 newtons on a mass of 50 kilograms. What can we conclude? Well, we easily conclude that the net force divided by the mass being equal to the acceleration, we have an acceleration A equal to net force divided by mass, 200 newtons divided by 50 kilograms, which comes out to be 4 meters per second squared in the direction of the net force. Okay? Now the units. How do we divide newtons by kilograms to get meters per second squared? Well, we actually define the newton to be a kilogram times a meter per second squared. This comes from the F equals ma statement of Newton's second law. Newton is a force unit, kilogram is a mass unit, meter per second squared is an acceleration unit. So what we have here are the units of mass times acceleration equaling the force units. If we divide the newton by the kilogram, we have kilogram meters per second squared divided by kilograms, which comes out meters per second squared. And that's how the units work in a situation of this nature. Now we want to consider, as an example, and obviously from the picture you can see that we're going to do this example by means of a diagram. Or at least we're going to do the example within the context of a diagram. Let's back up just a little more so we can see the whole document. Okay. Now, what we see here is a situation where we have a net force of 200 newtons on a 50 kilogram mass. That's the situation that we just saw. And that 50 kilogram mass accelerates from rest for 7 seconds. What can we conclude from this situation? Well, we saw already that 200 newtons, 50 kilograms implies a 4 meter per second squared acceleration. For 7 seconds, that's going to imply a change in velocity of 7 seconds times 4 meters per second squared, or 28 meters per second velocity change. And we're going to just be into a typical motion problem, which we already know how to solve and diagram and so forth. So here's a picture of what we have. We're given the mass, the 50 kilograms, the net force, the 200 newtons, the delta t, which is 7 seconds, and the fact that v naught is 0. Now it wouldn't matter if v naught was not 0. We'd still use the same diagram as long as we know v naught. We'll be able to average it later with the final velocity that we're going to find from all this stuff, and find the average velocity, which will multiply by delta t to get delta s. So what all can we conclude here? Well, we see that from mass and net force, as always, we can calculate acceleration. Then, knowing delta t, we can find change in velocity. Then, knowing v naught, we can find the final velocity. We put the change in velocity together with v naught to get the final, and then v naught and the final that we just found will give us the average velocity, which multiplied by delta t gives us delta s. And that diagrams the situation we see here. To do it again, 200 newtons, 50 kilograms, divide the net force by the mass. To get the 4 meter per second squared acceleration, we multiply that by the 7 seconds to get a 28 meter per second change in velocity. And we see those calculations carried out here. Now, initial velocity 0, delta v of 28 meters per second implies what? A final velocity of 28 meters per second. putting the initial and final velocities together, we simply average them to get the average velocity, 14 meters per second. And then an average velocity of 14 meters per second for 7 seconds implies that we move 98 meters.